Hey everybody, welcome back to another RevWise video. Today we have an IB Chemistry Center Level Paper 2 Specimen paper. It's been a while since I uploaded, just been busy with uni stuff, but we're back on the uploading schedule now because I know you guys have your exams soon. So yeah, this paper shouldn't be too difficult. We have our data booklet right here. Remember, you need your data booklet. And yeah, let's get right into it. Okay, a monoprotic acid HX is found to have the following composition by mass. CHO, and wants us to determine the empirical formula of the compound HX. So this is just a standard empirical formula thing. Remember, we're basically using our triangle with mass, molar mass, and moles, right? But in that triangle, instead of mass, we have this, right? We have our percentages. So basically, we can get the moles by using these percentages as the masses. So 39.99 over, and then for carbon we know that our molar mass is going to be 12.01, and then it's just the same thing all around. So for hydrogen it's going to be 6.73 over 1.01, and then for oxygen it's 53.28 over oxygen, it'll be 16. Okay, and that gives us our values of, this one will be roughly 3.33, and that will be 2, in this case this will be 6.66, right? And this one will be also roughly 3.33. And then when we simplify this, we know that we'll get 1 to 2 to 1, and that gives us the empirical formula of CH2O, which is our answer. Okay. 25 cm cube of solution containing 1.51 grams of HX is titrated with a 0.75 mole per dm cube solution of NaOH. HX solution is exactly neutralized by 22.3 centimeters cubed with the NaOH solution. Determine the molar mass of HX. Okay, so we know that it is exactly exactly neutralized by 22.3 centimeters cubed of the solution. So that means that the moles of HX is going to give us the moles of NaOH. And we know it's monoprotic, so it's going to be this it's easy one-to-one reaction, stoichiometry. So we have 0.75 moles per dm cubed. Mole dm minus 3. And essentially, we're going to be multiplying that, which is our concentration, and we're going to multiply that by our volume. So our volume is 22.3. Remember, this is in cm cubed, so that's going to be over 1,000. And when we do that, we'll get something that's roughly 0.0167, right? That's going to be our moles. And then we have our mass here. Our molar mass is our mass is 1.51. We have moles, and remember, mass over moles is equal to our molar mass is equal to 90.4. Remember, keep the units grams. State the molecular formula of HX. So molecular formula is pretty simple. Basically, you have to look at our molar mass, 90.4, and then look at our empirical formula, right? Because remember, empirical formula is the smallest whole number ratio. Molecular formula is basically all the actually includes all the atoms. So this molar mass is what happens, is the result of us counting all the individual mass numbers from our molecular formula. So essentially, it will be some whole number multiple of the molar mass of our empirical formula. So if we calculate our empirical formula, just do it roughly, it's 12, 2, and 16. So yeah, 12 and 2, right? That'll give us 14, and then plus 16, right? We'll get roughly 30, because we just used the rough numbers. And then 30, what does that go into? 90.4. So it's roughly 90 over 30, and that's going to be a multiple of 3. So how do we do this? We just multiply each number here, each subscript, we multiply it by 3. You can imagine the C and the O have a 1 underneath them, so it'll be C3, H6, O3. Yeah, there we go. HX reacts with the aqueous sodium hydroxide according to the equation HS, NaOH, okay, NaX, H2O. Identify a functional group present in HX. Yeah, just based on this reaction, we can see that it is reacting with a base to form this NaX, which is going to be salt and water. So we know that a functional group is going to have an acidic group, and that functional group is a carboxyl group, otherwise known as a COOH. There. Okay. Scientific model used to explain the structure of matter. Alpha particle is a helium-4 nucleus. In an experiment, alpha particles are accelerated towards a thin sheet of gold, and the resulting paths are detected, giving evidence of the positive charge of the nucleus. Okay, this is the Rutherford. Okay, the number of alpha particles detected at different angles of deflection theta are shown below. Okay, so these are the different angles of deflection, and the number of particles just makes sense. Okay, nuclear charges of gold and helium. So nuclear charge of gold and helium. Well, if you're wondering, right, you can look at the question for any context, right? But we won't really need nuclear charge of gold and helium. We just have to look in the data booklet for our periodic table. Can I flip this around? Well, it's fine. We'll just tilt your head bear with me. So gold, we see here, it has 79 atomic number. Helium has an atomic number of, where is helium? Should be here, no? Yeah, 2. Yeah, so basically it just wants, when it's asking for nuclear charge, it's basically asking us to write a plus in front of its atomic number. So plus 79, helium would be plus 2, right? Explain why some alpha particles follow path 2 rebounding from the gold sheet. Where's path 2? Okay, so it's this one. So it hits the sheet and it goes, it repels. So this is a thin sheet of gold, right? And what we're noticing is that a lot of it is just going straight through, right? Path 1, right? And we can see that some of them, path 2, it doesn't say here, but essentially a lower magnitude of these particles are being deflected. So why would it? Well, let's look at the nature of the particles. We have alpha particles. We know alpha particles is a helium-4 nucleus, and from here we identified it has a nuclear charge, a positive nuclear charge. We've also identified gold as a positive nuclear charge. Remember, all the questions are designed to help you get the next question. So from this, in our answer from I, we know that they're both positive. And what do we know positive things do? They repel. But what part of this gold is positive? Is it the whole? Is it the whole gold sheet? It's actually the gold nucleus, right? So what's actually happening? These alpha particles in path 2, these are the alpha particles that have come in close contact with the gold nucleus, this positive, strongly positive gold nucleus, plus 79 nuclear charge. And it's being repelled because they're like charges. So how can we say that? We can just say that these particles have been repelled due to close contact with the positive, this is a plus and VE, by the way, if that's confusing, positive gold nucleus. There we go. Most of the alpha particles follow path I and pass straight through undeflected, suggests a conclusion that can be made by the structure of the atom based on this evidence. Okay, so if you're familiar with this experiment, it's a pretty famous experiment, then you should know what the answer is. But if you're unfamiliar, it's just logical deduction, right? So we know that most of the particles follow path I and angle is 0. So essentially no deflection, right? Path I is just going completely straight. So majority of particles are going there, and only a few of them are being diverted or are going being rebounded. So why is this happening? Well, if you think about our atom, I won't draw it very well, but draw it like this, right? We know that somewhere in the atom we have a nucleus, right? We do something like this, right? Or the nucleus like this. Now, from this we know that most of the alpha particles follow path I and pass through undeflected. So most of the particles are going here, going here, going here, going here, only a very few is hitting here. And if these particles are being fired randomly, right, they're not being designed to go into this space, what does it tell us? It tells us that this nucleus is actually quite small. It's telling us this nucleus is a lot smaller than we think. And most of the atom is actually open space. So how can we write that in our answer? We can say the atom is mostly empty space. Very interesting, no? It's a great experiment. Okay. Helium was first identified by analyzing spectra of solar radiation. Outline the appearance of the emission spectrum of helium. Okay, this is a standard question. Just not really a fan of these questions because it's just memorization. If you know what you do, if you don't, you don't. But essentially, the appearance of the emission spectrum, just the standard emission spectrum appearance, it'll be discrete lines of different wavelengths or frequencies. I think you can say either. Yeah, it just consists of discrete lines of different frequencies and, well, or wavelengths. They both apply. Emission spectra of one-electron systems can be explained using a model with the electron attached to the nucleus by electrostatic force. The model predicts that the electron occupies discrete energy levels. Some energy levels for the helium ion are shown. Explain how the frequencies observed in emission spectra support the idea of the electron occupying discrete energy levels. So it's asking why, the frequencies observed in emissions. Okay, I understand. So it's asking why this support the idea of there being these n equals 1, n equals 2, n equals 3 type of energy levels. So why does this support it? Well, the energy of a photon, so this is the energy of a photon, by the way, yeah. So, spectrum. So each energy of a photon corresponds to a specific frequency in the spectra, right? And what else does this tell us? It tells this energy that we have of each photon, this energy is dependent on the difference in the energy levels, right? So we can see n equals 1, n equals 2. You can see this big difference, and then n equals 2 equals 3. You can see they're converging, but this energy is dependent on the difference in energy levels. This energy of a photon is dependent on the difference in energy levels. Yeah, that's a pretty simple one. It's just like a lot of this emission spectra stuff is memorization, so I'm not a big fan of it. A lot of them are just regurgitated responses, but yeah, you just want to say something along the lines of the energy of each photon corresponds to a specific frequency, and this the energy of the photon is dependent on the difference in the in these energy levels. So yeah, depending on the difference, there'll be a different energy of the photon, and then different energy of the photon, that is what relates to the different frequency, which what gives us this different spectrum. Ionization energy of helium ion 5250 kilojoules per mole, and the ionization energy of hydrogen is 1312 kg per mole. So just two reasons: the ionization energy of the hydrogen atom is significantly smaller than the ionization energy of the helium ion. Oh, wow. So many things you can say here, just simple things. First thing that you generally think about is when you're thinking about this atomic radius, right? So you have your data booklet. If you're not sure, if you can't think of it on the spot, just take a gander, right? Right. So hydrogen 32, helium 37, right? What does that tell us? It tells us the helium is just slightly larger atomic radius, but then we need to remember that it is a helium ion, and that positive charge makes its radius smaller. And that's what's going to make the hydrogen have a larger radius. Has a larger atomic radius. That's why you got to keep in mind, because a lot of people just go to the data booklet. They'll see, oh, helium 37, hydrogen 32. Wait, that doesn't make sense. Whether they told us that hydrogen has a lower ionization energy. So how does that make sense? Well, you have to keep in account that helium is an ion in this case, which means that there'll be a stronger electrostatic attraction to the nucleus, smaller atomic radius. Sorry, my room's a bit warm. I have to turn my AC down. Smaller atomic radius, so on and so forth. So yeah, hydrogen has a larger atomic radius. What else? Well, we can talk about the nuclear charge, because we just saw that H has hydrogen. I don't know, I keep saying H. Hydrogen has half, right? It's helium has 2, hydrogen has 1, so half the number of protons, right? So that equals lower nuclear charge. So lower nuclear charge, lower electrostatic attraction to the nucleus. That means that we're going to have a lower ionization energy. Okay. Suggest why the model outlined in BII can predict the emission spectrum of helium ion, but not helium. Well, that's just electron repulsion. Electron repulsion. Must be taken into account, because we're basically not taking that into account with this spectra, with this model, right? We're not accounting for these interactions that we would see these interactions in the He atom, but not in the He ion. So that's why. Outline why models of atoms have evolved over time. These are one of the nature of science questions they give you. I've seen so many of these. They have like hundreds of things on the mark scheme, and like any reasonable answer, they'll give you a mark. What can you say? Literally anything. So why have they evolved? There's been new technology, right? There's been new advances. There's been new findings, right? New evidence. I think they would even accept developments, like developments in recent models. Honestly, just say anything for this. It's a weird question, but yeah.